Welcome back. Good to see you all. Thank you for returning. I hope you enjoyed the first week. I just want to let you know I learned some things from it too, and I hope I'll do a little bit better job in some areas where I felt I didn't do so well tonight. Before we get going, once again, I will say a prayer. Okay? And this prayer, by the way, I will let you know, you listen to the words. It is intimately connected with something we're going to be saying toward the end of the evening, this evening, okay? So here's the prayer. In the name of the Father, and the Son, and the Holy Spirit, amen. God of the cosmos, your love reaches beyond space and time. We are astonished by your vast creation, innumerable galaxies, surrounded by elegant structures and staggering variety. The interplay of matter and energy, the pull of gravity, the speed of light, all showing your wisdom and glory, O God. We are dust and stardust, made in your image. We are the creation you are making new. Let our awe increase like your ever-expanding universe until we ourselves are lost in wonder, love, and praise. Through Jesus Christ, the Alpha and the Omega. Amen. I like that one. A quick summary of what we did the first session. I just want to just bullet points. I won't take much time. I'm just going to go to these rapid fire. First thing, we're now living in a unique generation of change. Only 3 generations before us. Everything you're feeling is real. It's really going crazy. Number 2, the faith-science conflict is more than false. It's an inversion of truth. It's a dominant postmodern myth. It serves the interests of the culture that's in charge. Number 3, the actual conflict is postmodernism's rejection of Western civilization's foundational pillars of philosophy and faith. 4th, many civilizations and many cultures existed before science. What they all had in common was a view that nature was chaotic, and they had mythical religions that they assigned to that chaos to make sense of their world. What are we? 5, science developed only in Christian Europe because of a synthesis of Greek reason and a Judeo-Christian God of law that enabled this culture to see order in nature unlike any other culture. 6, modern philosophical development after the cultural fractioning of the Protestant Reformation ultimately responded in increasingly atheistic and materialistic philosophy. The breeding of these ideas settled in and resides in academia. Whatever number 7, I guess, or 8. By the end of the 20th century, the culture of academia had become monolithically postmodern, which is to say, materialist and atheist. We're presently experiencing the full postmodern effect or effort to deconstruct Western civilization's cultural foundations and its institutions, its reason, its philosophy, its religion, its history, its law, and its governance. That's why our times seems so different. And last, postmodern science is now fully detached from philosophy, which gave it birth. It rejects in principle the existence of non-material reality outside its realm of study. It has become its own religion, scientism. Okay? That was last week. This morning, by chance, doing my morning reading of the Wall Street Journal, I just happened to pick up a page 1 article. Remember the funny video about the hoax that was played by those 3 professors? Here's the headline. Counterfeit studies are infecting scientific journals. The text, I'll just read a few lines of text. False studies have flooded the publishers of top scientific journals. The biggest hit has come to Wiley, a 217-year-old publisher based in Hoboken, New Jersey, which said on Tuesday it's closing 19 journals because of it. In the past 2 years, this floored me, Wiley has retracted more than 11,300 papers. Another outfit called IOP Publishing said in 2002 they detected 900 fraudulent papers. Now, these weren't hoaxes. These were just stuff that was just garbage that was coming at them. People, what they call slicing the salami or being paper mills, just publishing and publishing and publishing because you get the tenure, you get the money, you get the grants. That's what it is. So I thought that was fun seeing that this morning when I read that. Okay, ready to go? Okay. Make sure we got that going. All right. Where we stopped off, there was one thing I didn't get to talk about last week, and that was how that scientism got into the culture where we see it. So I'm going to pick up right there. By the late 20th century, there was a pretty decent conflation between science and technology. There had been so much technological process that in the minds of the public, it rubbed off on science. And science began to be perceived as something which we now know people call the science. It was just above and beyond what ordinary people do in most people's minds. It didn't work on preconceptions. It didn't have biases or belief systems. It was the science, And that became there. And what happened is that scientists inherited a deference that we kind of reserve for clergy. And they took it because they were becoming their own religion. You could see it happening. You could see this starting in the later part of the 20th century. 1980 was the year of Carl Sagan's Cosmos, which I loved, by the way, because I just thought Carl Sagan was so lyrical and poetical, and he was good. But maybe some of you remember the very end of the series. Carl Sagan's, if you did watch it, he goes by the shore, and he very poetically looks out and says, "The cosmos is all it is, or ever was, or ever will be." For you Carl Sagan fans, that's my bad impression. Okay, but that's the mainstream thought that is in there, and it's worked its way through. Now, that has advanced over time, and this man is Lawrence Krauss. He's a very popular physicist. He's published. He's worked with Hawking and other people, and you can see the advancement where we've got now. I'm going to let you read it, but I'll just read that very first line. Scientists do not have to know anything about what philosophers write. Philosophers need to know what we're doing. They aren't part of the program anymore. This is a rejection of a cultural history that goes all the way back. Even Stephen Hawking, you could see, he really went through a big change in his whole career. And by the end of his life, he died just a few years ago. In 2017, in his last book, The Grand Design, he made this famous statement, which ended, as you can see, philosophy is dead. This, to a lot of people, is an echo of Nietzsche's late 19th century statement, God is dead. Hawking was now saying, okay, now philosophy too is dead. So, materialistic, deterministic, scientism then proceeded to become what it is, a religion. Okay. I want to play for you a video to let you hear what this looks like from the inside. The lady that you see on the right is Heather Heying. To her right is her husband, Brett Weinstein. They're both evolutionary biologists. They're in the crosshairs of what's going on, very much. I'll tell you a little bit more about them later on. They are both Darwinian, agnostic, liberal scientists. I want you to understand that. They are very good people. Remember I told you, it doesn't matter where they come from. These are good people. Here is Heather's statement.
Many who speak of the science is settled, follow the science, think of themselves as secular. And the science that they are talking about is not actually science, but it is filling a religion-shaped hole. It is doing exactly the thing that these people who claim that they are not religious, what religion would be doing for them if they understood that instead of believing in a God, they are believing in a thing called science, and given the way they're describing it, they don't know what science is.
Some time ago, Richard Dawkins, who many of you heard on, captured the essence of scientism's materialism and what it means. And his quote is rather famous, that he characterized the universe as what we would expect. Nothing but blind, pitiless indifference. Not very encouraging. It goes further. Not only is the universe blind and pitiless, but some of you may know a guy by the name of Bill Nye, the science guy. Popular, I hate to say this, with young people and children. Here's Bill Nye.
I am just another speck of sand. And the Earth, really, in the cosmic scheme of things, is another speck. And the sun, an unremarkable star, nothing special about the sun. The sun is another speck. And the galaxy is a speck. I'm a speck, on a speck, orbiting a speck, among other specks, among still other specks, in the middle of specklessness. I am insignificant. I suck.
I would never want to join the American Humanist Association for fun. Even more depressingly, the determinism of scientism's members has taken it, for many of them, to the logical conclusion, when you follow this deterministic path that's saying everything is material and we're nothing but pieces of material, all the way to the point where now a substantial number have reached the point of saying we are now only living with an illusion of free will. We really don't have free will. The disagreement is to how much of an illusion it is in some cases. There's a tremendous price being paid for this philosophy and its enervating nature in life. And the message to this group at our age, which is predominant here, is that you probably are not aware of how much it is affecting young people. I'm going to show you some data. Take a look at this column here. And I want you to just focus on, you can see the US and Canada in red. And you'll see, this is a rank of happiness. These are ranked countries from the happiest Finland right on down. The first column is all people, and then it breaks it down by under 30 and over 60. And what I want you to look at is how huge the difference is in the United States and Canada as well. It's astounding how unhappy young people are. All kinds of statistics bear this out. A gentleman by the name of Professor Jonathan Haidt at New York University is becoming famous. He's a guy I've followed for years because he's focusing on this and bringing the data out and showing what's happening to young people. And in all the statistics you look at, it's affecting young people in a tremendous way. Haidt's book, his latest book, is called The Anxious Generation. Anxiety is shooting up. Suicide rates have gone up. And alarmingly, fertility rates are dropping rapidly. People think overpopulation is a problem. No, not in the Western countries. We're one of the countries that's actually in fairly good shape. Some are in terrible shape and going down fast. China's going down. Russia's in awful shape demographically. Some other Western European countries are. And you'll notice who's in the worst shape of all. Those who have lost their faith completely. In fact, the idea of children is thought of as a terrible idea because it's bad for the earth by a lot of people. Don't have children. Okay. I told you I always default to Bishop Barron and Word on Fire. And here's what Bishop Barron has to say about this. The fact. Oh, I didn't mention this. One of the outcomes from all of this is disaffiliation from the church. We all know how young people are leaving the church. That's an obvious outcome from the scientific age we're in. And Bishop Barron has something to say about the impact of that.
I'd like to connect Jung's insight to something we've discussed ad nauseum here, which is the rise of the nuns. If every psychological problem is ultimately a spiritual problem, and we have this increasing drift away from religion, do you connect that fact to the decline in mental health?
How can you not? And that seems so obvious to me. If you think for a minute that disaffiliation is kind of a harmless thing, young people, they don't care about religion. I'm not religious. I don't care about that. As Charles Taylor pointed out, so powerfully, this is unique in the history of the human race, practically. Human beings from time immemorial have been religious. Now, we debate about what kind of religion and all that, but they've all been religious. They're all related to some transcendent mystery or some transcendent good. We're the first generation ever in human history that is saying, who cares? I'm indifferent to that. Now, there have always been, the village atheists and all that, but in great numbers, isn't it now like 40 or 50% of young people say, I have no religion. And we think that's going to have no effect? You're running counter to this absolutely elemental human longing, and you'll have no problem with that. Give me a break. I mean, that's repugnant to everything we know about the human person. So no, I see them as deeply related to each other, disaffiliation and all this mental illness.
And as a person who's always been interested in catechesis and especially evangelization, looking at what the future portends, and these are the predictions, it's grim. That's why we have to deal with this, all the things that we can deal with that are causing this. I'm going to shift gears then and move on to what the future of this science and faith controversy, or at least what's posed as it, looks like. I already told you that the science and faith controversy is not for real. But there is a controversy going on. There is a real conflict going on. But the real conflict is within certain parts of institutional science. That is true. Not popular, but true. What's happened is that science, and I just want to define this because I don't want to blame every part of science. It's not the case. It's the parts where the metaphysical battle is being fought, the cultural battle is being fought. And those are in two areas. I'll get to those in a second. But it's happening in those areas because what the scientists in the area have been cut off from the classical roots that science has always enjoyed. And without it, it lacks the wisdom and the clear thinking of good philosophy. And it's subject to power, popularity of people with influence and ideas and groupthink. All these things happen when you lose your tether. There's one fellow that I've come across, a guy by the name of Ed Witten, who is called the physicist. He's ranked as next to God by people in theoretical physics today. He's thought of as the most brilliant guy there is in science today. The thing that's so scary about Ed Witten is nobody will challenge him. Everybody follows him, And what he's done is a 40-year history of taking throngs of people along with this thinking into an area of something called string theory. Anybody ever hear of it? String theory has been around for more than 40 years. It's got tens of thousands of scientists involved in it. It has absolutely nothing, there's no evidence it can produce because it only works in 10 dimensions. It can't even, in principle, provide something that's testable. And it keeps going on and on. And I've seen brilliant guys, one in particular saying, I'm afraid of him and I won't ever debate him because he's so smart. That's the thing that can happen, that kind of stuff. So one of the things that's happened being cut off from it is this disconnect from philosophy. But the conflict that's going on today is within physics and within evolutionary biology. Those are the two areas that are being impacted. The reason physics is impacted is because it's the grounding of all science. Physics is the science of what is reality, what exists, what is real. Every other science builds on physics. Literally, if physics sneezes, every other science gets the cold. It's one of those things. Evolutionary biology is in the crosshairs because it's the science of the universe's most complex feature, life. And especially because it's the source of life's most complex form, us. And we are the only form of life capable of comprehending reality. That's why evolutionary biology is in the crosshairs. This diagram here I've got up here is a good way of understanding how science works. Now, this is science as it normally works. I just want to use this diagram to illustrate something. In the upper left-hand corner is simply reality. This is a diagram representing knowledge. That's what it is. Here's reality in the upper left-hand corner. In the upper right-hand corner is what anyone, in this case science, says about what's reality. Okay? There's reality, and then there's what we think reality is. Those aren't necessarily the same. What science has, though, is a means down here at the bottom, which is the scientific method, which it uses to test what reality is. As you can see, the double-headed arrows there. The scientific method interacts with reality here, gets information, and is tested. Ideas are formed, hypotheses are tested, data is collected, and it then feeds back information to the scientists, who then can learn about what their method tells them and make better and better estimates of what is reality. That works well. It works wonderfully. The only problem is, I didn't put that up there. Excuse me. Forgot I had those in there. Okay, those are the things that I just said, okay? The problem is, when science says there is no non-material reality, it's making a claim called an ontological claim. Now, ontology is just a philosophical word for being. It's the science of being, what is, and what category of being is something that is, and that sort of thing. So scientism makes an ontological claim that there is no non-material reality. The problem with this is that it is doing this using the idea of non-materiality as a first principle, because being science, its method cannot test non-materiality, can it? So it's making a claim that it cannot test. So it's a self-refuting way of reasoning, but it's what it does. And this has been going on ever since the culture reached the point where the departure was made from the classics, from the faith and from the philosophy, and the kind of culture developed. Okay, what I'm going to do is let you listen to two different scientists, again on the inside, talking about what is going on in both communities, in physics and in evolutionary biology. The first guy you're going to hear is an English gentleman who's a physicist, and he went back to Oxford, where he was trained. And stood outside the halls of Oxford and did a reflection.
The 20th century was a truly exciting time in physics. From 1905 to 1973, we made extraordinary progress probing the mysteries of the universe: special relativity, general relativity, quantum mechanics, the structure of the atom, the structure of the nucleus, enumerating the elementary particles. Then, in 1973, this extraordinary progress stopped. I mean, where are the fundamental discoveries in the last 50 years equal to general relativity or quantum mechanics? When physics became a profession, a way to make a living, the incentives for physicists changed. Professions are always vigorously defended by the professionals whose livelihoods depend on it. In the case of physics, it's not just the practice of physics that has been defended, but the theories of physics too, as well as the language of physics. Sure, the trend towards professionalization began long before 1973, but to me it's no surprise that we've seen the effects compound over the last 50 years, as each generation of physicists has stymied the next with dead-end theories.
So the problem in theoretical physics has been a lack of progress. In evolutionary biology, the problem's been different. It's been the resistance to progress. And here, to comment on that, I'm going to use the same people, Brett Weinstein and Heather Heying, who are both professors, were professors of evolutionary biology and taught for many, many years. Again, here's their comments.
You and I were in Chicago together. I was there to talk to Richard Dawkins. I asked them why there had been no substantial progress theoretically. What was the last major breakthrough in evolutionary biology? Now, as far as I can tell, the last major development in evolutionary biology in the traditional sense was 1976. Ironically enough, it's Dawkins who, in his what I would call synthetic work, The Selfish Gene, makes a couple of kinds of significant breakthroughs, but he seems to misunderstand them. So when I asked them why there hadn't been a major breakthrough, they both told me that it was because their generation had solved all of the big puzzles and had been basically left a cleanup operation that didn't result in people making themselves famous in the way that Dawkins has become famous. That basically the field was solved. Now, I know, because I once believed that was true when I was a college student, and later came to understand that actually what had really happened was we had stopped talking about all of the big questions that evolutionary biology had not yet answered, all of the paradoxes it left on the table, is that belief that the field had reached a level of sophistication that effectively it was finished, is the sound of scientists claiming that science is settled. And it also became obvious to me in interacting with Stephen Myers and many of his high-quality colleagues that they're actually motivated, for whatever reason, to do the job that we are supposed to be motivated to do inside of biology. They're looking for cracks in the theory, things that we haven't yet explained, and they're looking for
all scientists are supposed to provide their own loyal opposition at some level. And scientific fields, increasingly, you are arguing, have abandoned that And so just as it's useful for liberals to have conservatives around on college campuses, it makes them smarter, and their absence is making them dumber, that the field of evolutionary biology, absent real critique, is allowing it to stagnate.
You see why people who don't fit your mold sometimes you can see are very good people? They're looking at reality, huh? Calling a spade a spade. By the way, he made a reference, Brett did, to Stephen Meyer and his good people at the Discovery Institute. Any of you ever heard of the Discovery Institute? They were roundly derided by scientists, and they, with a straw man argument, that they were like these creationists, young earthers, everything like that, when they're not. They're definitely a bunch of Christian scientists who got together, but they are the ones who are working. And you saw the reaction of Brett Weinstein saying, they're asking good questions. He's saying it. Why aren't we asking the questions they're asking? That's the kind of hope, that's where I'm seeing it, where it's taking place. Okay, I'm going to switch gears a little bit more and go to the state. A little bit I want to tell you about the state of each of those today, just to let you know where they are, okay? Because these are right in the crosshairs, these sciences. I'm going to tell you about physics first. And this isn't a criticism. I'm just going to tell you where it is right now. Physics is the science that seeks the most fundamental level of reality about the material world. About a century ago, its theoretical and its experimental work migrated to where it is now, where it functions at two levels vastly apart from each other. At the highest possible level, the cosmos, and at the lowest possible level, the inside of an atom. In fact, inside the nucleus of an atom. All physicists today work in one or the other. There's no way to cross between them because they're so different. And what's happened is that two significant discoveries were made by the large-scale folks studying the cosmos. One was in the 1970s. And what they observed was looking at the galaxies and using very sophisticated techniques, they began studying the rotational rate of the galaxies. Now, galaxies are enormous things, and they rotate, but it's really slow. Our Milky Way galaxy, for example, rotates approximately once every 200 million years. That's because it's so huge, okay? We're going around something like 40 or 50,000 miles an hour, from our point, just from that carried along. But it's so big. That's the reason it is. So they found out that all the galaxies are rotating too fast for some reason. And not by just a little bit. Some really fast, some moderately fast, but all of them too fast. And this was really puzzling. I'll come back to what they thought the reason was in just a minute. About 25 years ago, another observation was made. This was an observation that related to the expansion rate of the universe. Now, I think all of you have heard of the Big Bang, right? And you're going to hear more about it in just a few minutes. But right now, all of you can easily understand that it took place and the universe is expanding, right? And it has a rate of expansion. Studies were made to study the rate of expansion, to find out if we could determine if it was holding steady or not. Now, all the money in the house was on the fact that it'll be steady. Almost everybody thought it would be steady. A few folks thought, no, it's going to be declining. We're going to gradually slow down and maybe billions and billions of years from now stop and come back and have a big crunch. But they thought that would be due to gravitational effects. And there was logic behind that. What nobody expected was that the expansion rate of the universe was accelerating. And that's what they found. And nobody had any idea what could be causing it. So they had to come up with a theory. I'll go back to the galaxies first. The spinning, the heavier spinning of the galaxies, that was simple because the rotational rate of spinning, think of a figure skater who spins. If they pull their arms in tight, they spin fast. If you're light, you spin slower. Mass and spinning rate are well understood. So the theory was that there must be some matter, in fact, a lot of matter, in the galaxies that just don't show up. In other words, they have mass because they affect the rotation, but they don't reflect light or heat, and we can't see them. They called it dark matter. Have you heard of that? Yeah, now you know what that is. Okay, well, you know what we're talking about, right? For the expansion rate, the fact that the universe is accelerating, the only idea that they could come up with, and it is by far the dominant idea today, is that there is something in the very fabric of space itself that contains energy. And that this energy that exists within space, what we think of as empty space, though very slight, very, very slight, because there's so much space, is pushing the universe further. It's called the vacuum energy. And you're going to hear more about that too. And they call that dark energy. And what happened is they could quantify both of these. Because everybody knows the equation, E equals mc squared, right? It says matter and energy are equivalent. And I'm going to bring this back in just a few minutes, talk more about it. But because of that, you can put them on the same scale. In other words, you can weigh energy and weigh matter. You can actually do this. You can equilibrate them. And you can actually say what the universe we think is composed of now. And this is what we think is the composition of the universe. 74% dark energy, 22% dark matter, and only about 4% of stuff you and I think of as the real stuff. What a state to be in for physics. We can study about 1/25th of what the universe is composed of and don't know what the other 24/25ths are. That's the state. That's not a criticism. That's just a state that it's in right now. On the very, very small scale, what's happened is that simple atom that you saw if you took a chemistry class with a nice little nucleus of protons and neutrons and electrons spinning around, okay, that's actually been known to not be the case for over 100 years, or about 100 years. But the reason you didn't learn it and I didn't learn it, high school, colleges, what we know now is just too much. You got to get to the graduate level to really study it. This actually is a model of what's inside the nucleus of an atom now. And if you've never seen this, is it new to all of you? This is called the standard particle model, the standard model of particle physics. It's got all kinds of strange critters in there with funny names and weird properties. And it's not something that anybody could really talk about unless you got a few days to talk about it. Who came up with this? Some techies came up with these funky names, and that's how the word quark came in, and that's how the up, down, the charm. They just came up with funny names, and they stuck. You know, they should have come up with better names on it. They don't. But the problem is, this is not a criticism, but the problem is that this is a model of reality at the smallest level. There is a corresponding model of reality at the greatest level. The problem is they are in complete conflict. The smallest level does not contain anything that can relate to that dark energy, dark matter, or gravity even, that the world shows at any scale that's higher. So if anybody thinks physics doesn't have a long, long ways to go, it does. We're not anywhere near reality in physics. It's not a criticism, that's just where it is. And it needs, I will say, it needs its philosophical underpinnings so that it can get on the bus and start getting there. It's going down a lot of blind alleys with string theory and supersymmetry. There's another wacky model that's been proposed, and I was going to show a video, I didn't want to take the time. There's been tens of thousands of papers written about supersymmetry. They've got these big particle accelerators to test this stuff. They've been looking for supersymmetry for a dozen years, thousands of tests, and never found it, and they're still looking for it. And there's something philosophically wrong with that. So that's where physics is. Let's go to biology, okay? And take a look at that. And again, I'm limiting myself to evolutionary biology here. The real situation with evolutionary biology is quite different. It's the fact that so little change has occurred since Darwin's original idea. I don't know any other science like this that's made as little progress as evolutionary biology. Darwin's original idea that all inherited change comes from random mutation and natural selection has never been ever modified. It's still there. The only thing that's happened is we've gotten more specificity about what is it that causes the mutation. Where does the mutation take place? Shortly after Darwin's time, Gregor Mendel did some amazing work and found out that the cause of the mutations was, and he came up with the idea of genes, which has stuck. He's the person who came up with the dominant recessive, and his ideas are still valid. And by the way, anybody know what his day job was? Yes, he was an Augustinian monk. Yeah, another in a long line that you see, okay? And now the only thing we have today is since Watson and Crick did their famous discovery of the double helix of DNA, we now know that those genes are where they are in the nucleus of the cell in the DNA. But still, the only thing associated with this inheritance change, despite all the fabulous knowledge about the wondrous nature of living cells, is still confined to just this one little area, one macropolymer, DNA, in the nucleus of a cell. A living cell, literally, not figuratively, literally, is more complicated than the infrastructure of Manhattan Island. It's amazing. On the last day, I'm going to show you a video of how amazing a living cell is. And we haven't gone beyond that. Along the way, there's been things that just seem to come up against resistance. Again, this is this groupthink and this commitment that is just a resistance to change. There was a discovery that, as time went on, that very little of the DNA actually is functional. If you don't know this, the whole role of DNA is to make proteins. It does this by interacting with something called messenger RNA, which then generate proteins, because the stuff of what we're made up is proteins. Every part of us is made up of proteins. DNA does that job. Okay? The question was, why is there so much junk? Why is it I can't remember the number, I believe less than 5% of the DNA actually functionally codes for protein making. Why is the other 95% of it in DNA? Well, the original response, the kind of pushback response was, that's because in the human body, there's much more non-human DNA in your body than there is human DNA. Our guts and everything, we have all these critters that help us in our digestion all over us. So that's all in there. And over the course of all of our evolution, the thinking was all this stuff's gotten incorporated. We have all these friendly relationships with all these bugs that we live with, and that's gotten into our DNA. That was the pushback. What's happened, and what's still happening, because this is in the last 10, 15 years that this really got going, is found out that no, that stuff is not junk. They've figured out about another 20, 25% of it, and what it does. It turns out that it's not just the coding for the protein, you got to have control mechanisms. When do you turn on this gene? Where does this gene, and what cells does this gene turn on? And how does it turn on? It's like a control mechanism in any good process. You have to have features that control the making of the proteins. And they found out that that's what so much of this DNA does. And I'm sure they're going to learn a lot more as time goes on. There were other things too. There were other ideas of what's called non-inherited adaptation. This is just a picture of, on the left-hand side, some butterflies, and those are the same two butterflies. They're not different species. They're just different because they're exposed to a different environment. And on the right are some tadpoles that were only different because they were fed different diets, and they look quite different. And there's some real thinking is that we could pass down properties, inherited properties, that are not inherited from someone, from the parents of an individual, but it could be done during the life, and then it could be passed on that way, not through the Darwinian mechanism. That's been kind of rejected. There's been some other really good ideas. One amazing idea is called the third way of evolution, sponsored by a group headed by a wonderful scientist, a physiologist named Dennis Noble, who's probably in his 90s now. And this is a marvelous idea based on some wonderful ideas of chemistry and physics that says that other parts of the cell take in a lot of the random movement of water and solutes in the cell and convert this randomness into a projected actual change that affects the genome internally within the cell and can cause adaptation that the organism itself can't control. It's an exciting idea, but they don't want to hear about it for the most part. And there are other ideas too. And certainly I think somewhere, somebody's going to find something. But evolutionary biology just seems to be stuck. In fact, I'm not going to read this. I'll just let you look at it. These are all the areas where there's a lot of agreement that evolutionary biology has huge areas that need attention. They've all got issues. And the question is, why aren't people working more diligently on them? Why do they want to just stay with Darwinism and not move on? Okay? That's the issue. The complexity of life and its history should beget a real interest in doing it. Okay, so much for that. Let's move on. I want to go on to where... Oops. Something's happened here. Okay. There we go. Where the real challenge is going to be in physics and evolutionary biology. And where that's going to take place is in the area of consciousness. Consciousness is the real question, because this is the hardest thing to study. And with a predominant philosophy of materialism that says we're nothing but material, how do you accommodate for our consciousness? How do you accommodate for our rational thinking? How do you accommodate for all this? That's the challenge. We can understand the objective parts of our anatomy that give us, that we interact with our environment with, and we can understand how they send signals to the brain. Everybody can understand that there are sound waves being generated by my speaking that are striking your eardrum, and that your eardrum is creating electrical impulses that go to your brain, that you're seeing me, that light is bouncing off of me and bouncing into your eyes, going focused through your lens onto your retina, electrical signals being generated going to your brain, and that millions and millions and millions of cells in your brain are all flaring up with electrical activity right now. But why are some of them producing what you hear as sound? Why are some of them producing what you perceive as the depth of this room and me standing here? There's no projector in your head. There's no loudspeaker in your head. There's just signals getting electricity. No one knows. No one knows where this is going. And I'm going to skip.
To understand this, we have to imagine, for the sake of argument, that Nick...
Let me go back. I didn't mean to do that. I see that we're running out of time. I'm going to skip that, okay? And just go ahead. Sorry about that. I just see our time is getting limited. I don't want to miss out. I want to switch gears. And I want to move on now. That's the end of that whole section, building up. You heard this talk. We want to talk about the wonders. We want to talk about the changes. We want to talk about all the wonderful things that we can now see happening. And this section, I'm going to entitle right now, The Renaissance of the Teleological Universe. Teleology is another one of those big words in philosophy, and it means purpose. Purpose. In other words, I want to go directly against Richard Dawkins. It is not a pitiless universe. It's a teleological universe. And I think it could be a renaissance. The model for this is the first Renaissance. The Renaissance, we know, began back in the 12th century when some ancient texts were rediscovered. They were actually discovered in Arabic form because in the Dark Ages in Europe they had been lost. In the Arab countries they had found them and really admired them and studied them, and then it finally became known to the Europeans. After a period of reconciling this ancient philosophy with medieval Catholic theology, a movement grew. You may have heard of this, the Scholasticism movement. Okay, this is Thomas Aquinas' heyday, and that sort of thing that went on. This is also the time when the university came into being. The first universities all came in during that time. The system developed, and a desire to study nature developed at that time with all that information. And the study became known as natural philosophy, a term that stayed in existence through the 1700s, all the way through that term. This text is from a book on medieval philosophy, and this is the teleological nature of that period of time. The important point here is the manner of thinking of all of those involved was that they saw nature as a whole, saw it, and in it saw themselves and saw their place in it. This has always been the view of theology and of the Judeo-Christian world, all the way up through the scientific revolution. And this, with this kind of a philosophy, it would then bloom in the 16th and 17th century into the scientific revolution that we talked about. And as I showed you last week, I showed you Copernicus, Kepler, and Newton. All of them reasoned the very, very same way, the same as these scientists did. It was preserved all the way through about 1700. But of course, that has all changed in the following centuries, as we talked about. But I think the difference now is we've got so much new discovery that we're now in a position to finally, broadly, in the public domain, begin to rediscover that same kind of metaphysics that was good metaphysics that existed back then. And I think anyone who is a seeker of truth can attach to it. And that's how I got the name for this course. I know it's kind of science and faith, but the real name I had given to it was Science, the Creator's Emerging Great Witness, because I think it's there for us to witness in all of its detail. So now I'm going to go into a story mode, okay? And I'm going to tell you a great story. And it's the story of the Big Bang in all of its wondrous detail. It's a story that began about a century ago, and even though the cultural narrative has still got hold of us, it's a story that I think is going to begin to gain strength in the future. I call this an emergent cosmogony. Now, cosmogony is just maybe a big term. It just means the history of the cosmos. The fantastic thing about the fact that it had a beginning means that it has a history. Now, think about this. If we had an unending universe and everything's the same, there's no history, right? It's not interesting, but it's got a history. And boy, is it interesting. What we can learn from our history is really amazing, and that's the story. So we discover that our universe has a history. In fact, a whole new field of investigation did develop. And even though the cultural domination is still there, in the course of time, I think we're going to see this become a real means of pushback on the materialistic scientism of our day. Now, the time frame it unfolded, where it really took place, was the story goes back to 100 years ago. That's when the first quarter of the 20th century. This photograph I'm showing you was taken in 1927 in Belgium at a conference. It's considered a picture of the greatest scientists who ever lived at one time. This is the greatest power of thinking that ever occurred. You probably recognize at least one man there in the middle, right? Some of you who are into science will recognize quite a few other places. I'm going to tell you a little bit about that guy, Einstein, in a minute, but I'm also going to tell you about this guy, Max Planck, too, and something he did. And in the interest of time, I'm not going to tell you about other people. But let me start with Max Planck. I'm going to let you read that, and I put that text there just so you could understand the kind of man that Max Planck is. What the text really says is, here's a man in that same metaphysical mindset. Okay? There are still people who are doing the work. And it's not ironic to me that that's why the great men of science still were men of philosophy. And Max Planck was. What Planck discovered was something called the quantum. Now, I know a lot of you are here about quantum mechanics. What's the quantum? It was a discovery that when matter and energy interact, they do so in discrete quantities. It's not like light or heat is absorbed uniformly and gradually. It's actually absorbed or emitted, depending, in tiny little packets called quanta. That idea revolutionized both chemistry and physics. It was Einstein, again, you can read about Einstein. The text in red is one of his famous sayings. And what Einstein did was build on Planck's work, use that as a starting point, and he, as you know, y'all done reading? As you know, we all came up with this, right? It's so simple, and yet it's so profound. This is philosophically interesting, okay, besides being scientifically interesting. But what it says is that energy and matter are the same thing. And this is not in some philosophical sense. This is real. What you think is matter, us, the table, the floor, everything, it's not. What matter is highly, highly, highly concentrated energy. It's in a form called potential energy. And it's got forces holding it together in the nucleus of atoms. And that, we now know, is what energy is. That's why E equals mc squared. The interesting thing is that there must be a lot of m in the E, it must be a lot of E in the m, because it's times c squared. C is a huge number, the speed of light. Light travels from the Earth to the moon in about a second, so it's really big. If you just for curiosity's sake, if you want to know how much matter is in energy, I got this little tidbit of information that might be of interest. Suppose you could eat food, and instead of eating it and doing what we normally do, which is having a chemical reaction take place, where we get certain good things out and absorb it into our body, and the stuff we don't use, we get rid of, right? Which is our way of dealing with it. What if you could eat and convert all of the mass you ate into energy? How much would you need to eat? Well, it turns out, in a human lifetime, okay, in your entire lifetime, your whole diet would amount to 1/1000th of 1 ounce. That's how concentrated energy is in matter. It's that concentrated. It's an amazing finding that Einstein gave. And then in 1916, Einstein came up with another amazing discovery, which was general relativity, where, among other things, we learned what gravity really was. And if you don't know this, just fun fact, gravity is not a force. How often have you heard the force of gravity? It's not. It is just an effect of mass warping space and time. It's if you could picture a roulette wheel. If you put the ball in it, it starts to roll, and eventually it slows down and goes down. But just picture a roulette wheel with no friction, absolutely frictionless. No friction from the table, no friction from the air. If you pushed it, it would just keep going. And it would keep going because the area is curved out. That's how Einstein explained gravity. Well, it turns out that he did something. This is called Einstein's field equation for general relativity. Now, we're not going to get nerdy here. I just want you to look at that little circle that I've got there. That is the Greek letter lambda, and that is called the cosmological constant. And there's a great story about that, and I'm going to tell you that story now. So I just wanted you to see that because we're going to go into that. So we're going to go on and tell the story of the Big Bang. Now, the story begins in the late 1920s. A very obscure man gets involved, and he also gets involved with Albert Einstein. And I'm just going to let the story play.
The most profound discovery of our time is that our universe had a beginning and that it's expanding. Yet the person responsible for this discovery is virtually unknown, and there's a reason for it, which will become clear. Georges Lemaitre was a Belgian priest who theorized that the expansion of the universe began with the explosion of a single particle at a definite point in time faster than the speed of light. The Big Bang theory is accepted by nearly all astronomers today. But back in the 1930s, the belief that the entire observable universe began with a bang was considered preposterous. Even Albert Einstein found it far-fetched. An expanding universe completely shattered the notion that the universe was static, which is what Einstein strongly believed. But an unchanging universe was problematic for his own theory of relativity. If gravity were the only active force in a static universe, the universe would collapse. To get around this issue, Einstein added a cosmological constant, presumably a form of matter or energy that opposes gravity. On the other hand, Lemaitre's expanding universe would satisfy Einstein's theory of relativity. Still, Einstein wasn't swayed. He refused to believe in an expanding universe. Lemaitre recalled Einstein told him, "Your calculations are correct, but your physics is atrocious." It would take Einstein a long time to come around. He did finally abandon his cosmological constant, calling it the greatest blunder of his life. Lemaitre moved forward with his research and published a new paper in 1931 in which he argued that if the universe were expanding, then it also had a beginning. He proposed this in his hypothesis of the primeval atom. A primeval atom was a single particle. He argued that the universe began with the explosion of the single particle that gave birth to our entire cosmos, and concluded a creation-like event had occurred. Researchers date the event to more than 13.8 billion years ago. He didn't call it the Big Bang. Astronomer Sir Fred Hoyle coined the term during a talk broadcast on the BBC. Hoyle actually thought the theory was nonsense. Many scientists were skeptical, including Einstein. However, in 1933, when Lemaitre and Einstein traveled together to attend a series of seminars in California, and Lemaitre had time to explain his theory in detail, Einstein is purported to have said, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened."
Most scientists did not accept the Big Bang right away. It took a couple of decades till it became popular. It was really the 1950s when it finally got pretty well accepted. We're going to have more about Fred Hoyle, who you heard about in there. Fred Hoyle is the scientist who gave the derogatory name Big Bang. He gave it to it in a BBC broadcast in the 1950s because he didn't like it. He thought he was trying to put it down. That's where the name came from. Okay, the Big Bang itself has some wondrous things about it. The fact that it's a bang, the fact that it has a history, and then what happens during this history is so interesting. So let's take a look at the two wonders that we get from the Big Bang. Its history is one of those wonders because it's so intricate. And the second thing is what we learn is the significance of what's going on in that history. Here's a chart of the Big Bang, and it just shows the various stages from the very point of the Big Bang on the left to our situation, to our universe today. Now, this is an extremely exponential graph. It starts out at 10 to the minus 37 seconds after the Big Bang, okay, and proceeds to 1 microsecond, 3 minutes, 300,000 years, 200 million years, 400 million, 10 billion, and finally almost 14 billion today. And you see all these stages. It goes from being in an unimaginably hot, dense plasma to finally something which can gradually cool down to the point where subatomic particles finally begin to appear. And then finally the simplest atoms that exist, which is hydrogen, along with the second element in the periodic table, helium. And then finally the formation of stars, then the formation of galaxies, and then finally, much later, ourselves. That's the whole history of the Big Bang. And I won't take too much time going on it. The interesting thing about the Big Bang is its consonance with the Judeo-Christian tradition. Because it's a story, it's a consonance in two ways. The first way is the obvious one. It's a beginning. The universe had a beginning. And in fact, in the beginning, it was light. It was the first thing there was. It's so consonant. The second thing, which is not maybe appreciated very much, is that our coming into the story in both cases has a great similarity. We don't come into the story in both cases until the stage is set. And then we come into. You know the biblical story. I won't go over it. What I will tell you is something about the cosmological story and how that corresponds to it. Okay? And for that, to get to that story, we turn to the stars, the story of the stars. The ancients loved the stars. We all know how they looked up on a star on a quiet night, admired the stars, established the constellations, and just wondered about them and thought they were in some sort of a perfect sphere, a higher sphere. There was great wonder. My suggestion will be, if you listen to this, you might be in a position to say, we should have much more wonder of these stars because we know something about them they did not know. So I've titled this, something beyond what the ancients could have imagined. So in the beginning, everything in the universe was very, very simple. It began simply. And this chart here shows the life cycle of a star, all the life cycles of stars in general, which they begin just with the gradual accumulation of the hydrogen, the helium, which in space gets very cold, so it's dust, and it accumulates, and it gradually builds up gravitationally to the point where it's matter. The size is so great that the gravitational forces squeeze it down and create tremendous heat, millions of degrees, and a star gets born. And the nuclear furnace turns on, and the light comes. The life cycle that a star follows depends on one thing. How big was it when it was born? If it's very small, it's going to live a very long life. If it's very big, it's going to live a very short life. What's the life cycle range of stars? Some of them is as quickly as a few 100,000 years. And that's considered really, really short. Ours, which is a somewhat small media-ish star, is estimated to be a lifetime of about 10 billion years. Some small ones can live for trillions of years. But the interesting thing is what happens to them as they go through their life cycle. This line right here is the life cycle expected of our star. We're in this stage, the main sequence stage right now. 5 billion years from now, we'll get to this stage, okay? And we'll go through there. But what turns out is that these other cycles, especially the ones up there, the massive stars, boy, did they have a role to play. And we'll see that role. The thing about stars is that they're born and they live and then they die. And it's the living and the dying that are the important parts. In the Milky Way, about 4 new stars are born every year. And about once every 50 years, one of the big stars goes supernova. And it's the life cycle that matters. Here's a quick video about what happens in our star.
Way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself. And towards the center of that cloud, it gets denser and denser. It gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together. They start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out. And at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Okay. Being a soccer fan, and we had some problems, I'm going to claim some stoppage time, okay, and keep going here for a bit. Well, you can see what our sun is doing. Our sun is making some elements, right? A sun of our size is making carbon and oxygen, and that's about it. But you and I need a lot more than carbon and oxygen, don't we? Even though carbon, hydrogen, and oxygen are the principal elements that make up our bodies. In fact, we need a lot more than what our stars like our sun can make up. I hope this isn't too much for some of you who aren't chemistry fans or anything like that. This is a periodic table, and don't worry about it. These are just the elements from the simplest hydrogen up in the upper left-hand corner to all the other ones. The key thing here is that those ones which are colored are the elements that you and I need in our bodies. There are 58 elements that we need, and we need some stars to get to work to make these elements for us. One of the amazing things is the specificity that these elements have in our bodies. They can do a job that no other element can do, every one of them. And so all this thing does is the color code shows you the ones that are the most prominent. You can see carbon, oxygen, hydrogen, along with calcium and other elements that are there. But we need more than that. We need what the supernova can do. And this is a short video about what happens in a supernova.
The atomic elements needed for life to exist are produced inside the nuclear furnaces of the stars. But how do these life-giving atoms get from the interiors of stars to places where rocky planets like Earth can form? It's another amazing story of a universe that seems to have been built just right for life.
Well, nature has another trick up its sleeve. It's called supernovae. These are explosions when, in fact, for a short time, one star in a galaxy outshines the whole galaxy, and it explodes. To get the atoms out of the center of the stars, you have to blow up the star and distribute the stuff throughout the universe. The cosmos is seeded, therefore, through these supernova explosions with the atoms of life.
Supernovae have to occur in exactly the right way, or they will annihilate life rather than nourish it.
Conditions must be exactly right for the explosion of supernova. Too many supernovae, and there's no life in the universe. So these strange flicking fireflies of the cosmic night have to flick at just the right rate. Flick too fast, no life. It'll destroy all life in the universe. Flick too slowly, you'll have no carbon to build living things, okay?
We depend upon all these. In fact, there's as many as 6 different processes that the stars use to create the elements for life and for everything that there is. And we need all of those things to happen. What has happened here that's created life here is that long past, stars have gone through life cycles. Some supernovae have gone through life cycles. And in this region, near the Perseus arm in the Milky Way galaxy, where our solar system is located, some other stars went through their cycle. Some supernova went through their cycle. And a nebula of gas was there with all the necessary ingredients that began to accumulate and swirl, and slowly out of it came our sun and our planets and our Earth. And it took billions of years for all that to happen. That's one reason why the universe has to be this old to set the stage for us. The last thing I'll say is there's one more story I want to tell you, and then we'll depart. And that's the story of carbon. This is a little brief video from the very late, great John Polkinghorne. Some of you may know him. He's a scientist who became an English cleric, and he was a physicist. He's going to tell you a story about Fred Hoyle and carbon. This is amazing.
One of the great triumphs of astrophysics in the second half of the 20th century was to figure out how the elements are made. Because the very early universe is very simple, it only makes very simple elements. In fact, hydrogen and helium, the 2 simplest elements, and you can't really do very much with them. They have very boring chemistry. You need much more elements if you're going to have something as interesting as life, and in particular you need carbon. The chemistry of life is the chemistry of carbon. So where does carbon come from? There's only one place in the whole universe where carbon is made. It's made in the interior nuclear furnaces of the stars. Every atom of carbon in our bodies was once inside a star. We're people of stardust. Now, how that happened was figured out in Cambridge. Fred Hoyle, a senior colleague of mine, was one of the leading figures in this. And they were trying to figure out how carbon was made. They had helium, and if they could make 3 heliums stick together, that would make carbon. But they couldn't figure out how to do that. To get 3 small things like that to stick together at once, you can't do it. Okay, so we do it bit by bit, make 2 stick together, that makes beryllium, stays around a bit, another one comes along, makes carbon. But it doesn't work because beryllium is very, very unstable. It just disappears like that. So they were stuck. And then Fred had a good idea, and he said, it'll just go if there is something called a resonance, a very enhanced effect, which is just at the right energy in carbon to make that extra one stick on much, much more quickly than you would have thought. So he was very pleased with himself. We went off the nuclear data tables just to check that this resonance, this effect, was there, and it wasn't. And so Fred was a very stubborn, persistent friend. He rang up some friends and said, look, you've missed something in carbon. There's a resonance there that you haven't spotted, but I know exactly where it is because you had to have this energy. And they were apparently a bit reluctant to look, but in the end they went and looked and they found it. That's a wonderful scientific story. But also it struck Fred that it's more than a scientific story, because of course if the laws of nuclear physics had been a tiny bit different, either there would be no resonance at all, or it would be some other energy which would be no good. And Fred, who had a lifelong commitment to atheism, is reported to have said in the Yorkshire accent, beyond my powers to imitate, the universe is a put-up job. In other words, this can't be just a happy accident. This is too significant for that. There must be something behind all this. Because Fred didn't like the word God, he says some capital I intelligence has monkeyed with the laws of the universe.
Carbon is the only element that can build macromolecules, long molecules. We are just a collection of big molecules. Every one of them is carbon. We are carbon-based life. Carbon gets a bad rap now for a lot of reasons, but it's the essence of life. And this story about nucleosynthesis was known for every other element, the path, and they couldn't figure out the path for carbon. And they came up with this absolutely unbelievable long shot method and found out that that's how nature makes carbon. It's how it's done in the stars. And Hoyle said, how in the heck could that happen? We'll find more stories like that, okay? That's it.